In this recording, we're going to learn about polar and rectangular forms of complex numbers. So first, let's go with some familiar territory, the rectangular form of complex numbers, which may not be super familiar. So let's review. The rectangular form of a complex number would look something like this. A plus bi form. Okay, and again, this is the real component, and this is the imaginary component. Okay, so a rectangular number looks like this. We're going to look at the graphs of them right now. Okay, and again, a or b could also be equal to 0. Right? So let's check out the graph. What I'd like to use, and maybe you'd like to use as well, is a gizmo in explorelearning.com. So you have a login for explorelearning.com, but you may also just use the 5-minute free trial. You won't need more than 5 minutes. And what we're going to go to is this particular gizmo on the Argand plane, or the complex plane, also called points in the complex plane. You can just browse gizmos. And we're going to go to that gizmo. So what this gizmo allows us to do is plot some points. So I'm going to just randomly drag a red point out here, and it says that this point is 2, 5i. You can see the red coordinate right here. All right, again, the complex plane has a real axis and an imaginary axis. So just play with that a little bit. If you have this, drag a point out there, see what effect it is. Okay, so this one is -7, 4i. I'm going to put the blue one right on an axis. So this one's just called -4. There's no I part. It's not up or down. And this green one I'm going to put on a vertical axis. I'm going to put it right there. So this one's called -5i. Okay, so hopefully you can see, get a sense here of the points and the way the axis works. I'm going to try to export this and put this into our notes. Okay, again, take as much time as you'd like to explore that, mess around with those points, get a sense of how it works, and then sketch a complex plane in your notes, a real and an imaginary axis, and then plot some of those points, either your own points or these points, so you have a sense of how it works. It should be pretty intuitive. If you're saying, hey, this is not actually that hard, good. It's not supposed to be. It's pretty familiar because you're familiar with the XY plane. Okay, let's build on that familiarity and talk about what it looks like for complex numbers. So we're going to talk about some conversion factors. So first of all, you might have noticed that the a, we call about a plus bi, that's sort of the x, right? And we know that in polar form, the x is r cosine theta. So we're going to say a equals r cosine theta. Okay, it's like the x part. And you can probably figure out the b is r sine theta, because the b tells us how much we go up and down in this plane, which is like the y part, right? Next, okay, so again, let's kind of state what we have here. These are to convert from polar or trig form to rectangular. So again, this, we can call it polar form, or sometimes you say trig form of complex numbers. Right, but what if we want to go the other way around? What if we're given the point in rectangular form and we wish to convert it into polar or trig form? Well, that means we got to figure out the r and the theta, right? So again, the r would normally be the square root of x squared plus y squared. I think you may have that in your notes. So the x is now the a. It's just a squared. And then the y is now a b. So square root of a squared plus b squared. That's called the modulus of the complex number. Don't have to know that, but write it down. And then theta, also called the argument, Okay, and that's found by the arctan. Well, it used to be y over x, right? The opposite over the adjacent, but now the y is b and the x is a. And again, this is for a greater than 0. But if you have an a value that is negative, add 180 degrees. Okay? So our normal form of a complex number in rectangular form looked like this, a plus bi. But now we're going to make substitutions. We're going to replace the a with r cosine theta, because that's the x, and the b with r sine theta, that's our y. And then we're going to express it in our final form with the common factor of r factored out. So r, and then parentheses, we're going to factor out the r from each term. Cosine theta plus I sine theta. Okay, so that's considered expanded polar form. And there's also a condensed form, because it's always cosine some angle plus I sine theta, so sometimes they write it this way. The condensed form is this, r cis. They just take the c, the I, and the s from cosine I sine theta, and they write r cis theta. And that's called the condensed form. Box that in. Those are your complex numbers in polar trig form. So let's do a couple questions here. We're going to take a number in a complex number in polar trig form and convert it into rectangular form. So it looks kind of complicated. Let's break it down. All right, so give you a chance to write this one down. Okay, so if you paused and wrote this down, so we're going to name this complex number z, and it's equal to 7 times cosine 45 degrees plus I sine 45 degrees. These angles always have to be the same. They're our theta. So what do we know? Well, we know the cosine of 45 degrees. We can evaluate that. Let's grab our calculator, make sure we're in degrees, which we are, and do cosine of 45. 0.7071. Turns out the sine is the exact same thing, because it's an isosceles triangle. So the adjacent and the opposite legs are the same. So 0.7071. Let's head back over to our question that we're trying to convert here, and we will replace cosine of 45 with its decimal approximation. So, okay. Now I just need to distribute the 7. So to the nearest hundredth place, 4.95. Distributing that 7. So I'm going to box this in. We're going to use a rectangle for rectangular form. How do you like that? That way we'll remember that this is rectangular form. So we're going to do one other one, and then we'll check to see if this makes any sense. As a matter of fact, let's check this one now, just to get a sense of it. So if we have a radius of 7, angle of 45 degrees, let's see where that would be on our polar plane. How can we check our work? Well, if I'm going out to 45 degrees on a radius of 7, so 10, 9, 8, 7, I'm going to split the difference right there. So I have a point that's, oops, I'm not in the right place, 45 degrees. Let's get rid of that other point. What would that look like in a plus bi form on the rectangular coordinates? So if this is the real axis and the imaginary axis, well, what I can do is take that point and come straight down. So if I press shift on this point, it's got to come straight down. And if I hold shift, it will also go straight over. Okay, so what are the coordinates if this were like the XY plane, or the, let's come back up here, the real and imaginary axis? Remember, the horizontal axis is real. and the imaginary axis is the vertical axis. So back over here, well, isn't this 1, 2, 3, 4 pretty close to exactly 5? And that's exactly 5. So this point right here can be described as 5, 5, which is really close to what we got, 4.95 plus 4.95i. Okay, let's do one other and then we'll check it. So this one's expressed as 8 cis 30. So let's first expand that. Okay. Go ahead and evaluate cosine of 30 and sine of 30. Okay, so the sine of 30 is exactly half. Cosine of 30 is irrational. Okay, then I'm going to distribute the 8 to the irrational number. 6.93. Okay, and of course, we can check this one as well. 6.93 and 4i. Well, if I have 8 cis 30, that means I'm on the 30 degree, the radius of 8. Let's take that same technique of going straight down. I'm using this line tool. Put my cursor there, hold the shift down, it will go straight down. And I'll go straight across to the imaginary axis. And let's see if that makes any sense. My points again were a real component of 6.93, practically 7 for round numbers, and 4i. So let's see how we did. Okay, so that point, yep, it's just shy of 7. Some might even say 6.93 on the real axis, and then on the imaginary axis, yep, right on 4. So it seems like it'll make sense. Thanks for watching.